So before we begin the pH metric titrations and the curves, let's quickly recap buffers. Like I said, buffers will resist pH change. So again, one more time, just to make sure everybody's on board, buffers will resist pH change. What else do you know about buffers? They will contain a weak acid with its conjugate base, or a weak base and a conjugate acid. If somebody says, would you form buffers only if you have equimolar concentrations? Equimolar concentrations? The answer to that is no. That's a false statement. You can have buffers which will not have equimolar concentrations of the weak acid and the conjugate base. The only problem is that the buffer capacity there is going to be pretty low. So buffer capacity is not going to be good. So good buffers require equimolar concentrations. Yes, that's a true statement. And so let's quickly test ourselves if we can apply this concept to a question. The question is that you have a 1 liter buffer. You have 1 liter buffer, which is 0.1 molar HF and 0.05 molar sodium fluoride. And the question is, which action will destroy the buffer? Which action will destroy the buffer? And the choices are, if you add 0.05 moles of HCl, or would it be destroyed if you add 0.05 moles of sodium fluoride? The third one is if you add 0.05 moles of sodium hydroxide, and none of the above. None of the above. Realize sodium fluoride is a part of the buffer, so adding that is not going to, it will only improve the efficacy of the buffer. But what does sodium fluoride bring in? Sodium fluoride brings in fluoride. So you have 0.05 molar solution of fluoride, and you have 0.1 molar solution of HF. This is the weak acid, and fluoride is your conjugate base. The conjugate base is what is going to react with the acid HCl, and the weak acid is going to react with sodium hydroxide. So if you add 0.05 moles of sodium hydroxide, realize the concentration of HF that you have is higher, so the buffer is still going to be valid. On the other hand, if you add 0.05 moles of the acid, that's going to completely neutralize the base component of the buffer, and yes, that is going to basically destroy the buffer. So the correct choice is the first one, that the addition of 0.05 moles of HCl is going to destroy the buffer. All right, let's go further. Let's talk about the pH metric titrations in general. What do they look at? Things of that nature. All right, so like I said, titrations are a great way to assess a acid-base neutralization reaction. In reality, it doesn't always have to be a neutralization reaction. You can carry out a complexometric titration. You can carry out a redox reaction. In reality, a titration, the word titration, stands for your ability to determine the concentration of an unknown solution. That unknown concentration is what is called as an analyte. Okay? Now, usually this reaction, this method is used where you begin with a solution of known concentration, and this is usually a stable solution, the concentration of which is not going to change. Such a solution is what is referred to as a primary standard So if you recall the titration from your Gen Chem 1 experience, you probably would be thinking about a burette, which is that long tube, which is what is used to deliver sodium hydroxide into a flask that contains HCl, and you had 1 drop of phenolphthalein, which was basically your indicator to show you the end point, and you're seeking an end point of colorless to pink, if you can recall that. In terms of what kind of reactions we would be looking at, since it's a neutralization that we are going to study in this chapter, products will be water and salt. We've seen that before. And this can utilize strong acid, strong base. You can utilize weak acid, strong base. You can utilize strong acid, weak base. You would not be using the weak acid, weak base in this particular case. And the reason for that is because the neutralization doesn't go all the way to completion. You actually will never get good endpoint result or stark change from like colorless to pink. It's very difficult to do that. In case of a weak acid, weak base, it doesn't happen, and so you will not be able to use that to determine this experimentally. But the other 3 that we discussed previously in this chapter, those 3 are possible in an experimental sense to figure out. And of course, you guys ran both strong acid, strong base, and weak acid, strong base in Gen Chem 1 using an indicator. This semester, actually, the next upcoming lab is a potentiometric titration, in which we are going to utilize exactly that that idea. So going over this screencast is a good idea. Anyway, let's go further. So I want to discuss how we carry out a titration, and like I said, that basically we are seeking the end point. This is my burette. It's going in. This is a regular titration currently. It's going in HCl and phenolphthalein. Phenolphthalein is my indicator. It's going to tell me when the sodium hydroxide that's being delivered. So you're starting from an acidic pH, but as you add NaOH from the burette, it's going to start getting neutralized, and a point will come where it'll be completely neutral, which will be my end point or equivalence point. So one can say, what is equivalence point? Equivalence point is a point. Equivalence point is a point in titration. Point in titration where the moles of your base, that have been added are stoichiometrically equal to moles of acid. So that's a principal thing that you would know, that at equivalence point, moles of acid will be equal to moles of base, and this is a pretty important one. So irrespective of whether you are using an indicator for measuring this, or whether you're going to use a pH meter, which is a more sensitive way of doing this, equivalence point and what it is still means the same thing. Now, one can say that at equivalence point, really, the titration is complete. Beyond that, you're just going to, in a titrometric curve, you're just going to add more base to see how addition of the base is going to, change the pH. But really, the reaction is complete. Reaction is complete at equivalence point. All right, let's go forward. All right, so this brings me to what pH titration curves are. Like I said, you can determine, you can use an indicator to monitor your reaction, or you can use a pH meter to do so. But pH meters would measure the exact pH, and you can then plot that pH against the volume of the base that has been added, volume of NaOH that has been added. And it will give you a kind of curve. And depending on the kind of curve that you get, basically you will call that curve a pH titration curve, and or a pH curve sometimes. And so you can look at the kind of curve that you have obtained, and you can even make predictions. You can determine whether you were actually, if you had no idea about the experiment, you would still be able to tell whether it was a strong base, strong acid type of a experiment, or a weak acid, strong base, or a weak base, strong acid, or what. But realize that the progress will be monitored using a pH meter, which is a more sensitive and obviously more expensive method of determining the pH as well. And so let's take a look at some of the pH curves here. Now, like I said, we would be basically looking at 4 different types of titration curves. 3 we have seen previously. In addition, we are going to take a quick look for a polyprotic acid with a strong base. In terms of math, we are going to take a look at strong acid, strong base mainly, a little bit on weak acid and strong base. That too is up for grabs. But you should focus absolutely on a strong acid, strong base. So whatever I cover in the screencast, that's a good thing to follow, good rule of thumb to go by. But you should be able to recognize and label any titration curve for that matter. So what that means is that looking at a curve, you should be able to tell whether it's a strong acid, strong base, weak acid, strong base, weak base, strong acid, or whether we are dealing with a polyprotic acid. You should be able to tell that. So let's take a look at what to expect in each of these before the addition of the titrant, what happens at equivalence point, and what happens after the equivalence point has been surpassed. We are going to take a look at each of those and go from there. Now, the first curve that you're seeing is strong acid, strong base type of a titration. So this is, a system like HCl, which is being treated with sodium hydroxide. Your products are NaCl and water. Okay, so both HCl, that's a strong acid, NaOH, that's a strong base. Both of those are 100% ionized. So what that means is that we have in our flask or beaker, we have the HCl, right? So that's acidic, and we are going to add sodium hydroxide from the burette. Now, realize that before any base is added to the solution, that means at time 0, right over here, you have the pH, which is really low. In this case, it's almost approximately, one can say that this is close to about 1. So the pH is low, and that's expected because it's a solution of HCl. So that's going to be 100% ionized. You have a lot of your hydronium ion concentration. And as you're going to add sodium hydroxide from the burette, the solution is going to become less acidic because the sodium hydroxide that you're going to add from the top is going to start neutralization process. So this reaction of the base reacting with the acid, that's going to come into play. So notice there's an increase in the pH, but then right around, perhaps 40 milliliter, in this case, it starts a little bit before that, starts a little bit before that, but the rise in the pH tends to be pretty dramatic. And right when it approaches 40, notice there is barely any change in the volume of the sodium hydroxide that is added, but the pH is basically jumping. It's jumping from approximately, my guess is it's close to about 3-ish or so, all the way to 10. That's like a 7-unit change in pH. That's dramatic. So this point of inflection that you see right over here, the middle point of that is going to be called as an equivalence point. Now, because you have a strong acid, strong base type of a system, in this particular case, you can safely say that the equivalence point is going to lie exactly at pH of 7. And we know that because you know that the products in this case are NaCl and water, and NaCl is a neutral salt. So in case of strong acid, strong base, realize that it's a neutral salt. That is the reason that the pH is going to be 7 at equivalence point. And if you had to determine the equivalence point in an exam, what you will do is the following. If a curve is given to you, you're going to draw a tangent to the point of inflection right here. You're going to draw a tangent to the point of inflection right here. So that gives you the points, to sort of go with. And then you're going to determine the middle point of those points of where the change, the dramatic shift in the slope of the curve occurs. So the point of inflection in the middle of the curve is the equivalence point, and the pH changes extremely rapidly near the equivalence point. That means that even though we have not even added any additional base, or we have added very little amount, it's giving rise to large dramatic changes in pH. Now, if you continue to add in this region, if you continue to add the base, of course, now your solution is neutral, so any additional sodium hydroxide that is added is going to basically give you a basic solution, because HCl has been completely neutralized, and so excess base is just being added. So any added sodium hydroxide here is going to just completely remain dissociated to give you Na plus and OH minus. And so the exact shape of the pH curve that you get is going to be dependent on several factors, including the concentration, the strength of the acid, etc. And again, we are going to take a look at the math for this a little bit later, but I wanted to give you certain things to keep in mind. So again, realize if acid is what you have in your flask, because this is where you're going to put your pH meter. You're going to begin with an acidic pH, and that number is going to be pretty low. Usually, as a rule of thumb, you can say less than 2 is probably a good, but this is not, of course, set in stone, but usually you would see this number to be less than 2. The other way to sort of identify a strong acid, strong base neutralization reaction is that if you look at the point of inflection, essentially that is going to be pretty dramatic, and in this case it's changed from pH of 3 to even more than 10. It went all the way to 11 approximately, so that's like 8 units of change that's occurring. And of course, if you take the midpoint of that, that's a pretty significant one. That middle point will always be at pH 7. So if you see these key things, these key points, you can say that you probably are dealing with a strong acid, strong base neutralization reaction. All right, let's go forward. Oh, I should probably add, Just in case you would have started with a strong base in the flask and you would have added an acid from top. So if you had this kind of a system, that means sodium hydroxide is your sort of analyte, and your titrant, which is what is in the burette, titrant, then the shape of the curve is going to be opposite, is going to look like that. So just keep that in mind. So titrant is what comes from burette. Analyte is what is in the flask. Okay? All right, let's talk about the weak acid and strong base. And this picture that you're seeing, this is basically a pH curve where the red curve is for the strong acid, strong base, strong acid, strong base, so that's the HCl one. And I have basically plotted the blue curve, which is for the weak acid, strong base system. So the weak acid meaning something like acetic acid, which is being treated with sodium hydroxide, and you get sodium acetate and water. And I want you to compare a couple things here. So first off, recall that we said that in case of the strong acid, strong base, the starting pH before any titrant, any sodium hydroxide was added from the burette. So our system is still the same. The burette is where sodium hydroxide is, and your flask and the pH meter is in the beaker, or Erlenmeyer flask, however you want to say that. Or HCl is the acid is what is contained in that. So I said that in case of strong acid, the pH usually would be less than 2. And notice in the blue curve, maybe I should color code, the blue curve, I'm starting sort of approximately like 2.9-ish almost, slightly lesser than that. So that value is, pH is more than 2. So it's a higher pH that is reflective of a weak acid. That's the first thing. The other thing that I would like to point out here is that as you start to add the sodium hydroxide into the system, of course you're increasing the pH, but notice this really wide range and the sort of curvy line. It was pretty straight line in case of the strong acid, strong base one, but in case of a weak acid, there's a sense of a curve going through that, and that's pretty characteristic of a weak acid as well. I want you to also focus the point of inflection. Notice you go from somewhere around 6.5-ish or so to about 10. So that's about, 4 units as against about 8 units in case of the strong acid, strong base titration. So what we are saying is that this point of inflection is going to be pretty short in case of the weak acid, strong base titration. Of course, after the neutralization point, it doesn't matter. The rest of it is going to be just the addition of the strong base, so that's going to match up. The way you determine the equivalence point is still the same. So you would draw a tangent about here, the point where it starts to flatten out, and right here, and then you'll get the midpoint there. And that point is going to be the equivalence point in this range, which is denoted right here by point A. And notice, if you read that on the curve, that value is no longer 7. That value is actually almost close to 9. And what does that tell you? That tells you that whatever you have in the solution, so for example, sodium hydroxide, which would have reacted with acetic acid, that would have generated sodium acetate and water. And what do we know about sodium acetate? We know that the acetate from sodium acetate is mildly alkaline in nature. So the acetate is going to rip off the proton from water, it's going to give you CH3COOH and liberate OH negative. And so, since that is a strong base, your overall pH is going to be alkaline. Another way to say that is that sodium acetate undergoes hydrolysis. Because this is a titration where the base is strong, the overall neutralization is expected to be more on the alkaline side. Now, there are certain things or certain points that I want to kind of get your attention towards. And for that, I think I'm going to just, add a new slide so we are writing fresh and not lose this material. So just to kind of give you a flavor, we have the pH versus the volume of sodium hydroxide that is being added, which has been done in milliliters. And we go from 0 to maybe 100. So roughly here should be 50. We have 1. Let's say this is 12. That means half of that is 6. That means half of that is 3. I'm just kind of giving you ballpark a rough estimate of what it's going to look like. 4, 5, 6, and then 7, 8, 9, and then 10, 11, 12. All right, and our curve kind of started. Let me use the red one to show that it started around here. And maybe I should redraw that. So what I said was, in the beginning, our starting pH is going to be roughly around 3 or a value greater than 2, just as an estimate. Of course, as we add some amount of NaOH, it tends to increase. The pH tends to increase, and so it kind of looks like that. It looks like this. And what I said so far was, if you wanted to find out the point of inflection, you're going to have to find out the midpoint by first generating the tangent of the two points of inflections and read that off of the y-axis. So it's like 8.1-ish, and this is a rough estimate, of course. And I'm seeing that the equivalence point is approximately 41 for this setup. The volume that has been added is about 41. And we said that this point where it started, let's call it point A, that is the point where the pH is acidic and no sodium hydroxide has been added. And we said that, we talked about a couple areas. The area when you first start adding, let's say you add, about 10, 20, 30, whatever, 25. When you have added some milliliters of sodium hydroxide, the pH tends to rise. Absolutely, that is true. This region is sometimes what is referred to as the buffer range. And I'll tell you in a second why it's called so. Realize what's going on. You have acetic acid in your solution. You're adding sodium hydroxide. That means, in part, some of the acetic acid is reacting with sodium hydroxide and generating acetate. But where is that acetate going? Well, that acetate is just staying in that solution. So can I say that over a period of time, the concentration of this acetate is going to build up in the solution? And so a point of time will come where the molar concentration of acetic acid and the molar concentration of acetate is going to be exactly the same. So realize that this entire region, after you start the addition of the sodium hydroxide, because you're titrating a weak acid with a strong base, the added sodium hydroxide is converting a stoichiometric amount of the acid into the corresponding conjugate base. That means at any given point of time, you are beginning to build up a buffer. And the solution, which is a combination of the weak acid and its conjugate base, is now basically a buffer. And of course, if you wanted to, you can use the Henderson-Hasselbalch equation to determine the pH of that solution. That's always allowed. But realize that as this continues to build up, there will come a point of time where the concentration of acetic acid as well as the corresponding conjugate base are going to be equal. And this is what is called as this point of time where the concentration of the weak acid and the corresponding conjugate base, when those are equal, we call this point of time half stoichiometric point, sometimes also referred to as half equivalence point. Realize that if the base and the acid are equal and you plug this condition back into the Henderson-Hasselbalch, it's going to look like pH is equal to pKa plus log of A minus over HA. And by the way, since both of those are same, they are equal, they can cancel each other off, leaving log of 1. But what is log of 1? It's 0. So that term itself is not going to count. And you can simply say that the pH is going to be equal to pKa. That means at any given point of time, if you're able to measure the pH at that point of time, you would be able to determine the pKa of that solution. So again, realize 1/2 of the stoichiometric point or 1/2 equivalence point is that volume of sodium hydroxide at which 1/2 of the initial amount of the acetic acid has been converted to acetate, which has basically resulted in equal amounts of the weak acid and the conjugate base, which is why we have been able to say that the pH and the pKa are going to be exactly the same. So in terms of experimentally, how could you determine that? Since we know that the point of inflection, my equivalence point, so this was my equivalence point, since that was 40 or 1 milliliters, and this is, of course, I'm not using a ruler here, this is approximate, but in a real lab setting you would be using a ruler. Half of this 41 is going to be 20.5, so let's say that's about, if this was 30 and this was 40, so 20.5 is somewhere here. I'm going to extrapolate, and I'm going to extrapolate, and what I'm reading is roughly approximately 5.1-ish, 5.1. And so you can say for this type of, and again, it's not for scale, it's not to scale, but the way you calculate is what I want to drive the point across. You look at the equivalence point, whatever is the volume, just divide that by 2 so that you get the half equivalence point. In this case, that will happen to be 20.5-ish or so. And so extrapolate to read the pH. And since pH will be equal to pKa, you would say that 5.1 is equal to pKa. And so if you had to determine the hydronium ion concentration at that point of time, you would say 10 to the power of, or if you had to determine, let's say, Ka, because hydronium ion will be the pH. If you wanted to determine the Ka, in this case, you would say that that will be 10 to the power of minus 5.1, and that will give you the Ka value for this acid. So, or the system, essentially. All right. So again, if somebody asks you which is your, where is your buffer range? The buffer range is this region right before the point of inflection. Of course, your initial is when no sodium hydroxide has been added. Equivalence point is going to be in the basic region because that salt is going to be basic in nature. It's going to go through hydrolysis. And we learned something new. We learned about the half stoichiometric point or half equivalence point for the weak acid. All right, let's go forward. So again, if you had to summarize the key points, and I'm not going to, again, draw this to scale, but we have pH against volume. The shape sort of looks like that. This range is the buffer range. The midpoint is going to be the equivalence point. This point is your initial point. This region is where you have only sodium hydroxide, so that always is going to be in the alkaline region. What is happening between the initial pH and the equivalence point is that the solution basically becomes a buffer. The solution becomes a buffer. It obviously happens slowly because, as you're adding sodium hydroxide, that sodium hydroxide is going to react with the acetic acid and it's going to generate the sodium acetate in the mixture. So anytime you have the corresponding conjugate ion of a weak acid, you would say that a buffer is going to get generated. And if you have to, you can use the Henderson-Hasselbalch equation to determine the pH of such a solution. At half equivalence point, and again, the way you determine is you get the volume for the equivalence and you just go V divided by 2, and then you read that number by extrapolating on the y-axis, and at the half equivalence point, essentially the pH and the pKa are going to be exactly the same because half of all acid would have gotten converted into the corresponding conjugate base. So what happens this is what happens at half equivalence point. So then what happens at equivalence point? All of the acid gets converted to the A minus. That means basically the reaction, the titration is done. Anything past that, and that's going to be just the dissociation of sodium hydroxide, which is why the pH rises, and you just basically measure the pH of sodium hydroxide, the added sodium hydroxide. So again, realize beyond the equivalence point, you only have OH negative, which is in excess, and so that is all that you would be measuring in that region. Now, if you had to view a strong acid versus weak base, so something like maybe HCl versus, let's say, sodium carbonate, that is going to look like, you have a basic solution in your flask. So you're going to start with a basic pH. And notice it's a weak base, so notice how gentle that moves. So the buffer zone is going to be in this region, the buffer range. And again, the point of inflection is going to be pretty short, much the same way as we saw in case of the weak acid, strong base system. And if you continue to add HCl, you're going to basically be measuring the pH of the added HCl. So essentially, the main difference is that the curve starts basic and it has an acidic equivalence in this case, because it's a strong acid weak base system. So it's very similar in terms of what you expect. Now, I don't know if you paid attention in the previous curve as well, that each time I had, some indicators lined up for the system, and I just want to get your attention for that. Essentially, an indicator is an organic compound. Those are usually weak acids, which go from a protonated version to a deprotonated form, and that deprotonated form essentially gives you a color. So for instance, in case of phenolphthalein, when it remains protonated, it is colorless. On the other hand, when it loses that proton, it develops this really deep, intense red coloration. And if the change in color, the pH at which that happens, if that happens to match the pH of your titration, then you say that you can use that indicator for that particular titration. If not, then you won't be able to do that. So notice in this case, phenolphthalein essentially goes through a change between pH 8 to 10, and the way the curve turns, it misses that right before the pH change for the color is supposed to occur. The curve turns, and so you won't be able to use phenolphthalein for this system. On the other hand, if you consider methyl red, that changes color between 4.2 to 6, and that happens to match, it happens to line up with the equivalence point. So you would be able to track the reaction using methyl red as the indicator. In our previous case scenarios, we saw something different. So I'm going to take you back to that slide. So on this sketch, you are seeing again the strong acid, strong base in the blue, and you're seeing the weak acid, strong base in red. And I have two indicators here. I have phenolphthalein, which changes color when the pH is between 8 and 10, and I have methyl red, which changes color which at pH of 4.2 to 6. Notice phenolphthalein kind of overlaps with both the red curve as well as the blue curve. So phenolphthalein can be added as an indicator to both of your titration, whether you're using HCl versus sodium hydroxide, or whether you're using acetic acid versus sodium hydroxide. Phenolphthalein can be employed in both of those because this pH range is pretty high and it overlaps with both of those curves. On the other hand, for methyl red, you will be able to use that for the case of HCl versus NaOH. On the other hand, you will not be able to use it for acetic acid and sodium hydroxide. You won't be able to use it for that. And the reason for that is while it's changing color, the curve has surpassed that. So you won't be able to exactly track that in a very effective manner. So again, the choice of the indicator that you're making, that depends on whether or not the point of inflection matches with the point at which the color change takes place. So if you consider something like, let's say, let me give you a range, and you don't have to memorize these ranges, they will be provided to you. But let's say you have a range bromophenol blue, which changes color between 3 to 5. So bromophenol blue, and that changes color at pH 3 to 5. Do you think that could be used for either of the two titrations, the strong acid, strong base, or the weak acid, strong base? And the answer to that is yes, it can be used for the case of strong acid, strong base, because 3 to 5 means it's in this region. So it still matches the point of inflection. However, it's totally not even like anywhere close for the red curve. And so it won't be useful for the acetic acid, sodium hydroxide. On the other hand, if you wanted to use something like phenol red, phenol red, that changes color between 6.8 and 8.5. Now 6.8 to 8.5 is almost 7 to 8.5 right here. This is phenol red. Phenol red. Notice for that curve, again, there is an overlap. So phenol red will behave similar to phenolphthalein, and you would be able to use it in both of those cases. All right, let's take a look further. What you're looking at now is a polyprotic acid versus a strong base. So hopefully you can see that each time you have a point of inflection, that essentially tells you the number of protons that are being removed. So the first proton that is being removed is right here, the second one, and if you would have seen another one, that would have been the third. So in this case, the way it is, you would say that there are two protons that need to be removed. So this is kind of like a diprotic acid. Now, I also want you to notice another thing. The first point of inflection, notice the pH change was pretty dramatic. So this part essentially went from a pH of 3-ish to all the way to 8.5. So that's about a 5.5 unit change. Notice on the other hand, the second one is pretty short. And so you expect that if there is a third one, then it will be shorter. So if it's like just about 2 units, then the third one will be maybe just about 1 unit only. So the one thing that I want you to kind of understand for the part where we have the polyprotic acids is that you would be able to determine the number of equivalence points by just looking at each of the points of inflection. That's the first thing. The second thing is that the first point of inflection is always greater than the second point of inflection, and you will be able to see two equivalence points in this particular system. Now, the first equivalence point again in the titration will represent the titration of the first proton. The second equivalence point will represent the titration of the second proton, and the volume that will be required to achieve each of those is going to be the same. It's going to be identical. Of course, it will take harder, it will be difficult to remove that second proton, because now you already are trying to remove the proton from something which is already negatively charged, and that is reflected in the Ka, in just the inflection point. So the size of the pH change, it's reflected in that, but the volume that's required to reach each of the equivalence points is going to be identical. Okay, I have a question now. Let's say I have 3 titrations. Let's call it titration A, setting B, setting C. So in the first case, I'm titrating 25 milliliters of 0.1 molar weak acid, and it's a monoprotic weak acid. Monoprotic weak acid. And I'm titrating it with 0.1 molar sodium hydroxide. All right. In the next setting, I have 25 milliliter of 0.1 molar strong acid, and I have 0.1 molar sodium hydroxide. And the third case is that I have 25 milliliters of 0.1 molar diprotic acid. So that's a polyprotic acid. And I'm using the same amount of sodium hydroxide for that titration as well. So the question is, what can be said about the three titrations? So which one is true? All titrations have same initial pH. Okay, that's scenario one. The second one is all titrations have same pH at their first equivalence point. And the last scenario is all titrations require same volume of NaOH to reach their first equivalence point. All right, hopefully you can see that they cannot have the same initial pH because one is a weak acid, the other is a strong acid. So this is a false statement. Hopefully you can also see that at equivalence point the pH is not going to be the same, because we saw even the comparison between the weak acid and the strong acid. This is going to be at pH 7. This is going to be a pH higher than 7 because it's a weak acid, so the hydrolysis will take place. That leaves the last one. And so since the volumes and concentrations of all the acids is the same, the volume required to reach the first equivalence point is going to be the same for all three titrations. Of course, it's the first one that we are after. We are not worried about the second in case of the diprotic acid. All right.